Good afternoon, everyone. This is Advanced Thermodynamics and Combustion by NPTEL, right? So, uh, we are into the fourth live tutorial session of this course. And the theme of today's discussions is thermodynamic property relations uh, in line with the contents of this week's lectures. Okay, and the instructor for the course, as we all know, is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. And I myself am from IIT Guwahati only, a research scholar, and also a Prime Minister's Research Fellow. So we shall start in another couple of minutes, right? Let's wait for a few minutes to see if others join, and then we can start today's session. Thank you. Okay, so we can start today's session. So as I have already mentioned, today we will be discussing thermodynamic property relations. So in this week's content, there are two lectures, right? So scheme of the session will remain as it is. So first we will discuss topics that have been covered in this week's lectures. And after that, secondly, we will have conceptual questions. Okay. And then at the end of this session, we will have a few numerical questions. Also, because in this week's content, there are two lectures only. Yes. So, so maybe we can uh, devote more time on the topics that have been covered because we have to because I have to take this session for 2 hours anyhow, right? So in that case, I'm planning to have a bit uh, uh, more discussion on the topics. But obviously, we'll have questions also. Okay, so let's see the topics first. Okay, so there is lecture 10, right? So majorly three topics, three headings, discussions have been done on uh, around three headings. First one is mathematical formulation of properties. Then second is Maxwell relations, and the third is thermodynamic property relations. So the whole idea of this week's content is that we want to have the properties, different properties of our system, and we are studying some system. In that case, different properties linked to that system, we want to calculate it by mathematical formulations. So suppose we do some experiments uh, on our system, right? And then we acquire some data, maybe in terms of pressure or in terms of temperature, right? Or in terms of volume, we acquire data, right? So using all that data, how can we find other properties linked to a thermodynamic system, right? Maybe it can be enthalpy, it can be entropy, right? So in that effort, the whole discussion for this week has been done. Okay, so under mathematical formulation of properties. So under mathematical formulation of properties, a brief introduction has been given on how what we will be doing in the whole lecture, right? And then two important diagrams have been introduced. One is your PV diagram, and then another is your PT diagram, right? In terms of phase change, right? And for these two diagrams, water H2O has been taken uh, as a fluid for discussion. Right? Okay. So first is PV plane. So it is something like this. So in this diagram, what we do, we draw isotherms, right? Isotherms means lines where the temperature will remain same. Though P and V will vary along these lines, but the temperature for all this during all this change that we are showing through isotherm, temperature remains same, right? Okay. So this region is one where we have liquid vapor both coexisting, right? And this is our critical point. So all these are isotherms. So for these isotherms, the temperature will be greater than critical temperature of water, right? And for these that are below this critical point isotherm, for these cases, temperature will be less than critical temperature, right? Okay. Just wait for a second. I'm going through something. Some reference. Okay. So after that, we have a PT plane, right? So what happens in PT plane? So in PT plane, we have isometrics, right? And what are isometrics? Isometrics basically are lines where we have a constant specific volume, right? So So if we are discussing water only, so these two critical points are same, but in the above diagram we are because drawing P versus V diagram, and in the below we are drawing P versus T diagram. That is why there is a difference in it, right? And to the left of this line, line joining the triple point and critical point. To the left of this is liquid phase, and to the right of this is gaseous phase, right? Yes. And this we have as critical specific volume. And the specific volume to the left is less than critical specific volume, and to the right is greater than critical specific volume. So the whole idea of using the diagrams only is that the things become very easy to visualize if we have the diagram in our mind. So in that case, it becomes easy to analyze our subject of interest. Okay. So these two things have been discussed in this topic. Okay, majorly in the mathematical formulation properties. Then comes the very important topic of this week, that is Maxwell relations. Right? So one by one we shall see uh, how we get our Maxwell relations. Okay. Very important topic. Very, very. So, so to have discussion on Maxwell relations, first we will have a small discussion on exact differentials. So basically, the idea of introducing an exact differential into the discussion of this Maxwell relations or mathematical relations for thermodynamics is that exact differentials are those in which the integral is dependent on only the states, right? So it doesn't depend on the path that is system is taking to move from one state to another state, right? So in that case, if we have state functions, so those state functions can be defined using these exact differentials, right? And then we can dwell onto the mathematical formulations using those state functions and exact differentials of those state functions. Okay, so this is the whole idea. So this is there is one property of exact differentials, right? So let's say if we have some function z, right, that is function of x and y. In that case, its exact differential can be written in this way: partial differential of x with respect of z with respect to x when y is constant, right? Then partial differential with respect to y when x is constant. So this. Now what we will do, we will call this as n, and this we call it as n. Right? So there is the property of exact differentials. Okay. So this property, specific property, we shall be using to derive Maxwell relations. So this property is dou y of m when x is constant equals to dou y dou x of n when y is constant. So this is a property that we need to keep in mind. Okay, when we are deriving equations, Maxwell relations. So now coming to the Maxwell relations. So Maxwell relations have been derived using four equations, right? So two are this TDS equations, right? One is your Helmholtz based on Helmholtz function, and then one is based on your Gibbs function. Okay. So if we see our first uh, Maxwell relation, so it is based on a TDS equation, right? So this is first is this. Okay. Now in this case, if you compare it, because if you see on the left hand side, we have written a B, right? It means internal energy is an exact differential, right? And then we can property related to exact differential we can apply here, right? That is this property. Right? So in that case, here if we compare it with this dou m by dou y, dou by dou y of m and dou by dou x of n, in that case, we see that our m is t, right? And n is minus p, right? Yes, and x is equivalent to s here and y is equivalent to v here. So now if we write this dou by dou y of m thing, so it becomes dou by dou v of t, right? At constant s equals to dou of minus p, sorry, by dou of s, right? That is at constant what v, yes. So it becomes dou, so it becomes this, right? Yes. So this is our first Maxwell relation. Okay. So this is based on what? TDS equation, right? So this is a TDS equation. Then we have second Maxwell relation, that is dH equals to TDS plus VdP, right? So here M is E, N is V, X is S, Y is P. So it becomes dou T by dou, dou T by dou P, right? at constant s equals to dou n by dou s at constant p. Okay, sorry, I have written n directly. So this n is v. Okay, so this is your second Maxwell relation. And the third is based on your Helmholtz function, right? So this is minus p dv minus s dt. Here m is minus p, n is minus s. Okay. Then x is v, y is t. So it becomes dou minus p by dou t at constant v equals to dou of minus s by dou v at constant t, which becomes dou t by dou t at constant v equals to dou s by dou v at constant t. Yes. So this is our third Maxwell relation. Then the last is Maxwell relation is based on Gibbs function. So this is our Gibbs function, right? Here m is v, n is minus s, x is p, y is t. So it becomes dou v by dou t at constant p equals to dou minus s by dou p at constant t. That is dou v by dou t at constant p equals to minus dou s by dou p at constant t. So this is our fourth Maxwell relation, right? So this way we defined Maxwell relations. Okay. Now the next heading is thermodynamic property relations. Okay. So in it, what we do is, in addition to Maxwell relations, we define a couple of other relations also. Okay. And how do we define those relations? So this is thermodynamic property relations. Okay. So from this topic, first we discuss basic relations, and then we discuss additional relations. From this basic relations, we get 8 equations, right? From Maxwell relations, we get four relations. From here we get 8 relations. And to get these 8 relations is quite easy. So how do we do that? So firstly we will see uh, internal energy, right? Specific internal energy, which is a function of S and V, right? So what we can do, we can write its exact differential as this. We can split it this way, right? Now, how do we get these 8 relations, right? So I'll write this way. I'll write another 3 exact differentials, okay? And from each such exact differential, we will get 2 relations, right? So if we compare it with our first Maxwell relation, right? This. So we know du is also equals to TdS minus C PdV, right? In that case, if we compare these two, right? If we compare these two, what do we get? Dou U dou U by dou S at constant V equals to T, and dou U by dou V at constant S equals to minus P, right? So this is what we get, right? So these are two relations. First is this and then second is this. Same way, if we see enthalpy, okay? Enthalpy is a function of S and P, right? In that case, its exact differential will be written in this way. Dou H by dou S at constant P ds plus dou H by dou P at constant S dp. Okay. And now if we compare it with this, the second Maxwell relation, then what we get is dou H by dou S at constant P equals to T, and dou H by dou P at constant S equals to V. So these are two more. Okay. Then third is your this psi, that is function of specific volume and temperature. So it becomes okay. So comparing it with this third Maxwell relation, what we get is And so these are two more. Then coming to the last, Gibbs function. This is a function of pressure and temperature. In that case, its exact differential becomes constant pressure Pt. Now comparing it with fourth Maxwell relation, that is, this gives and minuses. Okay. So these are your 8 basic relations. Okay. Two are here, then two more here, two more here, and then last two. So these are 8 basic relations. Then the same way, what we can do, we can compare these, right? So, for example, we can compare T from first and second, right? Then we can compare P from first and third. Okay. The same way we can compare this specific volume from second and fourth, right? And then specific entropy from third and fourth we can compare. In this way we can get our 4 additional relations. Okay. Okay. So this is about thermodynamic property relations. Okay. Maybe I can write the 4 also. Okay, let's see. If at the end time allows, we will write it at the end. Okay. For the time being, we will just move ahead. Okay, so this is about lecture 10. Okay. Then moving on to lecture 11 of week 4. So here what we have done is, so now that we have our relations, 16 relations, we have thermodynamic relations. So what we will do, we will have discussion on phase change processes. Okay. And for that, we shall be taking help of Maxwell relations. Okay. And this way, we shall have a discussion in this particular lecture. So, as the first topic suggests, is that we want to evaluate the property change. So, when there is a phase change, the properties linked, right, to the change of state. So, evaluation in that context, we shall be doing in this particular lecture. And for that, two equations have been introduced. Okay. First equation is Clapeyron equation, and then second equation is Clausius-Clapeyron equation. So these two equations kind of similar equations. Uh, the difference is that the Clapeyron equation is just an extension of a special case of Clapeyron equation. So then is so under this heading, first we saw phase change processes, right? Relations for phase change processes. So this basically is a TDS equation using which we will define our phase change process, right? So in case your phase change process is taking at constant pressure, in that case the TDS equation can be written as dH equals to TDS, okay, which essentially is, so subscript G and F here represents gas and fluid, okay, or liquid, fluid or liquid. T Sg minus Sf, or Sg minus Sf equals to by T. So this is your in case of phase change process, specific entropy and specific enthalpy. How do we define? Right? And similar way, if we want to define internal energy change, so that we can do by this particular relation, right? Which is, so all this in one way or another is TDS equation, right? So these are two relations in connection to phase change processes. Okay. Now, so we discussed our this pressure temperature plane, right? Or phase diagram. In that case, there is one point, right, where liquid and gas are coexisting, right? So what this particular point has effect on the partial differential dou by dou t of P at constant volume. That is also the slope of this particular graph is that it becomes a exact differential. Okay, so this can be written this way. Right? Now, what is a Clapeyron equation? So from one of the relations that we derived, right? So if you see your third Maxwell relation that we have derived from this Helmholtz function, right? Yes. So it says that, so if you see your Maxwell relation, okay, I'm just writing three from the context of our this sessions discussion. Otherwise, you can in any order you can name these relations, right? Because we have done this particular relation in third order, so I'm writing it three. Okay, so this is, what is this? This is dou P by dou T at constant volume equals to dou S by dou V at constant temperature. Yes. Now, as I have said, for saturated states, it becomes exact differentiation. Okay. So in that case, it becomes saturated equals to this, right? And now what we can do is we can from here find out this change in the specific entropy, right? Just cross multiplication and nothing else of the above relation. So this becomes Vg minus Vf. Okay. So now we have, if you see, we have this C and this B, right? So if we compare these two, what do we get? From C and D, what do we get? We get, right? So this is your Clapeyron equation. This is your Clapeyron equation. Okay. And then if you see your Clausius-Clapeyron equation, what we have done in it, the, sorry, the second 11.2, 11.3, sorry. So Clapeyron equation is basically we take two approximations to the Clapeyron equation, right? One is that specific volume for the fluid is zero, right? And then specific volume for the gas can be treated using ideal gas equation. Okay, considering the pressure of it is very low, right? In that case, what do we get? If we take the Clapeyron equation, right? So, so this becomes Okay, so this becomes 0, right? And then what do we get? PVG, right? And VG, as we have seen, can be written as RT by P. So it becomes RT square by P. Okay. So this is your Clausius-Clapeyron equation. Okay. So now if we take this P on the left hand side, so it will get some a bit different form. Okay. But essentially it's one the same thing. Right? Okay. Then we have phase change diagram. Sorry, phase diagram. So it is something like this. Okay. So three curves are there. This is sublimation curve. This is fusion curve. This is vaporization curve. Here we will have solid state. Here we will have liquid state. Here we will have gaseous state. Okay. So fusion means from direct solid to from solid to liquid. And then vaporization is liquid to gas. And then sublimation is from solid to gas direct. Okay, so this is your phase diagram. Then we have 2 points. Okay. This point is your triple point where all the three phases coexist. Okay. And then this is your normal melting point. So this is your phase diagram. Okay. So discussion on how the transitions take place, all this has been done in the lectures. Right. So this was your discussion on the topics that we have covered in this week's lectures. Now moving on to questions. So we shall now quickly move on to questions. So first let's see conceptual questions. So first question is here. So please, we can try to answer this. This is from first topic of your lecture 10, mathematical formulation of properties.
Uh, it's uh, uh, it's negative since it's an isotherm.
Okay, okay, so Pranav says negative. Okay, so this is question number 1, and it says that on a PV plane with single phase region, the slope dash at every point on the isotherm excluding critical point. So options have been given, four options have been given. First is the slope is positive at every point. Second is slope is negative at every point. So third is it is zero at every point. So it can be positive, negative, or zero. So the question asks about PV plane. Okay. Then this is single phase region. Okay. Then this is slope. Then it talks about every point on the isotherm, and we have to exclude the critical point. Right. So we have seen the PV plane. You see here, we have the PV plane, right? So the isotherms, including the isotherm which includes critical point, and the isotherms above this isotherm that contains critical point, right? For these isotherms, okay, if we see the slopes, so we know how the slopes work, right? Right? So if you have line like this, it will be a positive slope. If you have a line like this, it's a negative slope. From the tan. Slope is basically tan. Okay. So if you see this particular diagram, in this case, for the single phase regions, this is the slope is negative, right? So the answer to this will be negative only. Okay. So this is about PV plane. So this question is on critical point from the same PV plane. It says that this.
It's zero, right?
Okay. So so again, this question is on PV plane and then single phase region, right? That is for all the isotherms above the critical point isotherm. And then the slope is either positive, negative, zero, or it can be anything. So if we see our this slope, right? So at critical point, so it will be the slope of this PV diagram will be zero. Right? So it's a kind of flatness at this particular point, right? So if we see the curves on the left and right of this particular point, so there is this flatness in comparison to this left and right curve, right? And for that uh, reason only, if we find the derivative at this point, right, it will be zero. Okay. So the answer to this is zero only. So all other options are incorrect. So it can be positive, negative, or zero is not the case. It will always be zero. Okay. So C option is correct. Okay, so it's already 4:02 p.m., right? It's already 4 o'clock, 4 o'clock. So we shall have a small break, 5 minutes break, and then we can continue the session. Thank you.
The slope should be zero and pressure is constant.
Okay, so let's continue with the session. So this is question number 3, and this again is on mathematical formulation of properties from lecture 10. So this question again is on PV plane, and the options are these.
Option C is zero and independent.
Okay. So the question says that on a PV plane, two-phase region. The two-phase region, it talks about slope, and then it talks about pressure. Okay. So if we see our PV plane, so it talks about such cases. Okay. So here if you see the shaded region is the region where two phases coexist. Okay. So in it the curve is firstly flat. Okay. So flat means the slope is 0. Right? And then because it's a flat curve and on y-axis we have pressure, so that implies the pressure remains constant for this part of the curve. Okay, so the slope will be 0 and the pressure is because constant. So, so, so if you see this diagram, so here the specific volume, so if we take 2 points A and B, so if we move from A to B or B to A, in that case the specific volume will change but then pressure remains same, right? So the pressure is independent of specific volume. Okay. So it will be this C option. So Pranav is right. Okay. So moving on to next question. Yes.
The slope is positive, right?
Okay. So the question says the pressure temperature plane or diagram, that is also phase diagram. Okay. With single phase region, the slope is dash at every state on the isometrics. So what is isometrics? Isometrics is constant specific volume. So let's see the diagram. So this is your PT plane, right? So if you see the isometrics for different cases, you will realize that in all the cases the slope is always found to be positive, right? The slope means dou by dou t of p at constant specific volume. Right? Yes. This. So for this PV plane, the slopes for isotherms were negative for single phase regions, and for this PP plane for single phase regions, it is uh, positive. For this, it was negative. For this, it is positive. So A option in that case is correct. Okay. So moving on to next question. So this is a true or false type of question.
It's true because at every temperature there would be like in the two phase region the slope would be zero, so it's true.
Okay. So you're saying in two phase region the slope will be zero. Okay. So first question talks about slopes in isometrics. Corresponding to specified temperatures. So if you see this diagram, okay, so in this, let's say we have this point A here, right, where liquid and gas phases are coexisting. Because from here only these are diverting to different isometrics, right? So in that case, first of all, this partial derivative becomes this full differential. Okay. And secondly, the slope will not be zero. Okay. For PV plane, you can say that, right?
Oh, yeah, sorry, I
Yes,
accidentally
yes,
imagined the
yes.
PV plane instead of PV.
Yeah, because I have the question says that isometrics talks about isometrics. Here we deal with the isotherms. Okay. So those slope won't be zero, but it will be finite. But for this point, these two will have same slopes. Okay. So if question says that yes, for a specified temperature, let's say we have some temperature at a point, right? Where this liquid and gas phases are coexisting, right? In that case, both will they will have same the slope, right? Because it's the same point where this two phases are coexisting. So it will be a true statement. So moving on to next question. Differentiate. Yes, we can try to answer this. So this has been exact differentials have been discussed in Maxwell relations topic. Okay. So while I was discussing this topic in the topics section of the session, that is the previous session section. So there I told that The idea of using exact differentials in thermodynamic studies is that exact differentials are path independent. Okay. So the integral will depend only on the initial and final states, right? So if we know the initial state, if we know the final state, in that case we can easily find the integral of that exact differential. Be it the differential of internal energy of enthalpy, right? Of Helmholtz function or of Gibbs function. So if we want to analyze our thermodynamic system using these properties, right? And we want to find these properties. So in that case, exact differentials can prove to be very handy. Okay. So exact differentials are independent of path. So in that case, this because the question says dependent, it's a false statement. Okay. Okay. So moving on to next question. So this is from lecture 11, property relations for phase change processes. And this question number 7 says that the evaluation of changes in specific entropy, internal energy, and enthalpy accompanying a phase change process is obtained through which of the following equations?
I think it's Clapeyron.
Yes. So we discussed Clapeyron equation, and then there we discuss so how if water changes from gas to fluid, right, or vice versa. In that case, how these thermodynamic properties of the system change, and we derived it using a Maxwell relation. Okay. The basic idea of it was, so here it is Maxwell relations. So through this tedious equation, first we got the change in specific entropy and change in specific enthalpy relation, right, which is equation C. And then we, through Maxwell relation 3, we got this change in specific entropy and change in specific volume D. And then we equated C and D, and this is how we got Clapeyron equation. Right? So if you see Clapeyron equation, so change of specific enthalpy we can find out, right? So equation your this question says that specific entropy, internal energy, and enthalpy. So enthalpy we can find out, right? And if you see this your C equation from here, you can see that specific entropy also you can find out, right? And then Specific internal energy also you can find out from this relation just below C. Right? So in that case, this B question, B option becomes correct. So this is very straightforward question. But the whole idea also is that we with solving questions, so all these topics just go through our mind and we are able to also revise these topics. Okay. Yes. So question number 8 is that the Clapeyron equation shows that the slope of saturation line on the ET plane, that is phase diagram, depends on the property change signs of which of the following. So this is Clapeyron equation we have to use, and then we need to find the slope of saturation line. Okay, so what is the saturation line? And then the saturation line is on ET plane. So property change signs. So if some property is changing when we are moving from one state to another, the sign of that, whether it is positive or negative. So the slope depends on which of the property change signs of which of the properties. Okay. So if you see your phase diagram, PT diagram, right? So this is your saturation line from triple point to critical point, right? And this is your Clapeyron equation. And the slope is d by dt of p, right? That is the slope of this dt plane, right? So this have we have mentioned that its slope is d by dt of p saturated. So if you see in this Clapeyron equation, so d by dt of p is the slope, and then we have a change in enthalpy and change in specific volume. These two properties are there. So whatever the sign of these two changes will be, the slope will depend on that one, right? The sign of slope will depend on that, right? Though we have already seen that it will be positive, so it means that the signs of these two properties will be in such a manner that the d by dt of p at constant specific volume is positive, right? So here, if you see specific volume and specific enthalpy, this third option is correct. Okay. So moving on to next question. Yes, we can try to answer this.
I think it's option A. We neglect the liquid phase volume, then we get the equation.
So this is a Clausius-Clapeyron equation. Okay. So the Clapeyron equation can be modified to obtain Clausius-Clapeyron equation using which of the following approximations. So here, first is that the specific volume in liquid phase is negligible in comparison to specific volume in gaseous phase. Okay. Then specific volume in gaseous phase is negligible in comparison to specific volume in liquid phase. So out of these, because these two are opposite to each other, so one is correct out of these. So this option A is correct out of this. But then there are other two statements also. Third statement is the pressure is low enough so that the specific volume of gas phase can be obtained from the ideal gas equation. The temperature is low enough so that the specific volume of gas phase can be obtained from ideal gas equation. So out of these, this C option is the second approximation. Okay. So the pressure is low enough such that we can consider it an ideal gas equation. Okay. So this we can try to remember. Okay. So in case pressure is low, so specific volume we can obtain using this ideal gas equation. That I have already also written while I was discussing Clausius-Clapeyron equation. So first approximation, if you see A point, is that specific volume for fluid or liquid is zero or negligible in comparison to V subscript G, sorry, V subscript G. And then B point is that specific volume or gaseous phase, we can try to, we can do it using ideal gas equation. That is PV equals to RT. Okay. So then we placed it in Clapeyron equation and we got our Clausius-Clapeyron equation. So in this case, both the options A and C will be correct. Okay. Okay, Pranav. Then moving on to next question. So I have total 13 conceptual questions and then two numericals. Okay. So this is from phase diagram heading.
It should coexist with it, just with water.
Just for water. Okay.
Just add it down. Like, like
Yes.
I have seen that, like physically, practically, I have seen some kind of fumes when we handle some ice. Like, is it vapor phase or like don't know.
That I believe you are talking about dry ice. You're talking about dry ice or what?
No, no. Like while I'm handling some ice, like the water,
Okay.
solidified water. So
Yes.
like there are some fumes or some like
Yes.
cold
Whatever
vapors. I
is
think I don't know. Is it okay?
the vapors, if it is uh, getting condensed, maybe that you're talking about. If the surrounding this because the surrounding also have the moisture, and when it that moisture comes in contact with this some cold object, in that case it starts to condense.
Okay, okay. Like there is some heat transfer, so
Yes, yes,
that's why.
yes. Okay, so this question is from phase diagram. Okay, so this is sample of ice and then normal melting point, it says, and then coexist, it says, with which of the following? With air at standard atmospheric temperature. So this question is from this this topic. Okay. So here on the fusion curve, we have normal melting point. Okay, and this fusion curve is boundary between solid and liquid, right? Solid is your ice, and then liquid is your liquid water in case of H2O. Okay, so the ice will be coexisting with the water, liquid water, at normal melting point, because the normal melting point also is on the fusion curve. You can see that. Okay, next question. So this again is from your phase diagram topic only. The slope of fusion curve for water is, so also there is, if there is increase in melting temperature, in that case that happens when we do what with the temperature of water.
Should be the slope is negative, and the other one is increasing temperature.
Okay. So the slope will be negative, right? But in case of water, what happens is there is this decrease in temperature that will result in the increase of melting point. Okay. So for other cases, when for some fluids, fusion curve is positive. So in that case, the second fill in the blank will be increased. Okay. So to increase the melting temperature, there should be an increase in temperature for the fluids where fusion, the slope of fusion curve is positive. But in case the slope of fusion curve is negative, in that case, the decrease in temperature will result in an increase of melting temperature. So this will be D option will be correct. So moving on to next question. The negative slope of fusion curve of water emphasizes that, yes, which temperature will be higher in comparison to which temperature? When we are,
Triple point temperature is the higher than normal melting point. Normal melting point at 1 atm pressure. So, triple point is greater than normal melting point
when we
temperature.
are, yes, when we discuss this phase diagram topic, so in that case, these two points have been described. Okay, the triple point and the normal melting point. So if you see the diagram here, so this is your normal melting point and this is your triple point. So T for normal melting point clearly is less than the T for triple point. This is T for triple point and this is T for normal melting point. Right, so T for Tp is greater than T for N. That the triple point is greater than the normal melting. The options. Okay, so moving on to next question. This is one phase diagram. The depression of the temperature of triple point of ice to that of temperature of its normal melting point is referred as regulation. Whether this is a correct term or not, please. Fact-based question. Okay, so this is a true statement. Okay, so this is called regulation. So if temperature is moved from triple point to normal melting point. So moving on to numerical questions. So first is this question. Let's try to solve this. So we need to find out dou by dou v of S at constant temperature for water vapor, which is having a temperature of 220 degrees Celsius and a specific volume is also given. Okay, and then use the given equation of state and an appropriate Maxwell relation. Okay, okay. So, so some parts are missing for some reason. Okay, so this is your equation of state. Correct. So we need to use this equation of state and then we need to find out dou S by dou V. So what we will do, I just start solving this. Okay. Temperature given is 220 degrees Celsius. So question 14. So we have been given dou P by dou T at constant volume is given as R bar by minus B plus A by 2V. This is equation of state which has been given to us. And then P is 3 by 2. Right? Not a big deal because equation of state already is given to us. So we have been given specific volume which is 0.4243 meter cube per kg. So we will convert it into meter cube per kilomole, right? As per our other terms that have been provided, right? This is in this, and then because molecular mass of water is 18, okay, so this comes out to be 7.64 meter cube per kilomole, right? Then if you see temperature is 220 degrees Celsius. That is 273 plus 220 equals to 493 Kelvin. Okay. Now we are good to go. So we can directly place dou P by dou T at constant. Why I'm solving this is because what have been asked by the question. Okay, so from the Maxwell relation, that is equal to this dou by dou T of P at constant volume. So now we will just place the numerical values. Okay, so this is 7.64 minus this B is given to us. Okay, B is given to us, then plus 142.59 divided by 2 into 7.64 this into V plus B. That is 7.64 plus 0.0211, right? And then T is also given, that is 493 raised to power 3 by 2, right? And then 110 raised to power we will add here to uh, convert the bar into Newton per meter square. Okay. So if we solve this terms, first term comes out to be, you can try to solve this, right? If there is some mistake, you can let me know. And then the second term will come out to be 1, 2. And if we solve this comes out to be 1102.35 joule per Kelvin. So this is your question number 14. All right. So then moving on to next question. Okay. So previous question was on Maxwell relations. This question is on Clausius-Clapeyron equation. Clausius-Clapeyron equation also is indirectly on Maxwell relations, because here we have used Clapeyron, this Maxwell relation, one of the Maxwell relations. Okay, so water has been given at 22 degrees Celsius. Then pressure temperature curve, right? At saturated conditions, that is PT plane. From PT plane, it is there. So this is in kilopascal, temperature is in Kelvin. Specific volume has been given in SI units. Then specific volume of liquid is negligible. So you have to use so this is the first approximation, right? That V subscript F is 0. Then Clausius-Clapeyron equation we have to use to find the enthalpy of evaporation. So Clausius-Clapeyron equation. So dP by dt saturated equals to enthalpy of evaporation. So let's say enthalpy of evaporation as EE. Okay. Then that is also Hg minus Hf, right? Which is also Hg minus, or let's straightforward question. RT square by P. Okay. Yes. Also, this is Hg minus Hf by TVg minus Vf, right? Now slope is given to us. slope is given to us as 0.162, and Hg minus Hf, enthalpy of evaporation, we have to find out. Temperature has been given as 493. Sorry, has been given as 22. Right? 22 degrees Celsius. That is essentially 295.15. Right? And then Vf is 0 and Vg has been given as 36.23. Right? This implies Hg minus Hf becomes 0.162 into 295.15 into 36.23. That comes out to be 1732.31. Okay, so this is your enthalpy of evaporation. Okay, at 22 degrees Celsius. So this will be in kilojoule per kg only, because your this d by dt of P is also in kilopascal by Kelvin. So 1 kilo we have. All right, so this is your last numerical, and we are done with it. Okay. So let's conclude the session. So this session was basically about thermodynamic property relations. So in the first lecture of this week, that is lecture 10, we saw different relations. For in different relations, we saw four Maxwell relations, eight basic relations, and then four additional relations based on the basic relations. Okay. Then in the next lecture of this week, that is lecture 11, we saw discussions on phase changes. Okay, phase changes in terms of Clapeyron equation, in terms of Clausius-Clapeyron equation, and later in this lecture we saw a phase diagram where uh, different curves were shown, right? Curves, namely sublimation curve, fusion curve, and vaporization curve. These three curves were shown on the PT plane, right? Okay. So these discussions were carried out using with the help of Maxwell relations only, right? So here we did uh, 13 conceptual questions and two numerical questions. Numerical questions were on Maxwell relations, and then Clausius. One was on Maxwell relation, and one was on Clausius Clapeyron. And in this way, we carried out this session number 4, live tutorial session number 4. So we have come to the end of the session, right? And so thank you for attending the session, and we shall meet in the next session. Also, the next session I have preponed because of some unavoidable reasons, right? So the next session will be on Saturday from 10 to 12 a.m. Right? And till then, yes, okay. So till then, keep learning, right? Happy learning and goodbye. Okay.
Yeah, thank you.
Okay.
Bye.